Good evening, everyone. I welcome you all to the Student Research Seminar Series 2021. My name is Devyani and I will be the host for the evening. This event aims to showcase the research done at IESc publicly. This will be a monthly event and today we are inaugurating its very first talk on codes for the input constraint binary erasure channel by Arvind Rameshwar. This event is organized by IEEE-IISc Communication Society in collaboration with the IEEE-IISc Signal Processing Society. Let me give a quick introduction to IEEE. IEEE, which is the, as you all know, is Institute of Electrical and Electronics Engineers, was founded in 1963, and it is a professional association which organizes multiple workshops and conferences across the globe. Communication Society is an independent society of IEEE since 1972 with over 200 plus chapters in 142 countries. The society provides services for technical and professional advancements like interaction with experts, access to resources, magazines, etc. This society also provides forum for technical exchange among professionals in academia, industry, and public institution. Therefore, we would encourage you all to become a member and avail the benefits. To become a member of IEEE IISc Communication Societies and Signal Processing Societies, you may please contact Varki and Abhijit. The mailing IDs are mentioned on the left side. The membership is absolutely free of cost. Okay, so just for the records, we would like to know how many of you are an IEEE member here. So I would request you to quickly raise hands so that we can get a count. Okay. 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 Thank you. You may unraise yourself now. Thank you. Now, let's begin the talk. Today's talk on codes for the input constraint binary erasure channel by Arvind Rameshwar. Without further ado, Arvind received the Bachelor's of Engineering degree, honors degree in Electronics and Communication Engineering from BITS Pilani University, India in 2018 and was the gold medalist of the graduating class of 2018. He is currently pursuing PhD degree at Department of Electrical Communication Engineering at Indian Institute of Science, Bangalore. He is a recipient of Prime Minister's Research Fellowship 2020 and was a part of the team that won the Qualcomm Innovative Fellowship India 2020. His research interests lie in information theory and coding for finite state channel. Welcome, Arvind, and the floor is all yours. I'll stop sharing and you can share your screen now.
Thank you. Yeah, I'll share my screen now.
Yeah.
All right. Okay, firstly, thanks a lot to all the organizers for having arranged this talk. This being a communications talk, there is a fair amount of emphasis today on the applications end of things. So if anything, what one can take away from this talk is primarily a coding scheme, okay, for the case with feedback of a certain input constraint binary erasure channel. Okay, we'll be specifying what this coding scheme looks like and what is the specific input constraint that we are dealing with, etc. Okay, so let's get ahead with the talk. So this talk concerns itself primarily with the familiar model of a discrete memoryless channel or a DMC. But the only different thing in this talk is that the DMC now has inputs that obey certain hard constraints. Okay? So we all know that DMCs are particularly familiar models for noisy communication, wireless communication. So it's also used to model storage media such as hard drives, disk drives, etc. And the specific constraint sequences that we have in mind will be different from the power constraint sequences that are common in communications. In particular, the constraint sequences that we will be dealing with are those that are found in storage media particularly. For example, to give you a particular instance of where this is true, for instance, if you want to store an amount of data on, say, a hard drive, um, it is necessary that the high voltage pulses that represent ones or one inputs on that are to be stored on the hard drive are spaced sufficiently apart. And the reason being, so suppose if you space these two high voltage bits very close to one another, then there's a good chance that both of these bits will sort of coalesce with one another and there could be intersymbol interference. At the same time, you don't want these two high voltage pulses to be spaced too far apart, because then what would happen is that the encoder and decoder could lose track of synchronization. Okay, so these are the kinds of constraint sequences that we will be talking about. Find application primarily in the maintenance of synchronization markers, etc., in multimedia streams. And they also arise as natural constraints in biological storage media, such as DNA storage. Now, where this comes out to be true is in DNA synthesis, it is well known, it's a well known fact, that among the four nitrogenous bases, A, T, G, and C, the concentration of the guanine and cytosine nitrogenous bases shouldn't exceed more than, say, 50%. Okay, this is for reasons that have to do with the stability of the DNA molecule. So, in order to, synthesize DNA molecules that respect such a constraint sequence, hard constraints are used as ways of modeling this constraint. Okay. So again, what is our setting or our communication channel that we're interested in? This is our well-known discrete memoryless channel. Okay, so just as a reminder, you have a message M that is needed to be sent by the encoder, and the encoder, what it does is it translates this message M or maps this message M to a sequence of input bits xn. And then these input bits are then sent across the discrete memoryless channel to get an output sequence yn, and the decoder uses these yn output bits in order to get an estimate m hat of the original message. Now, why is this channel discrete memoryless? It is memoryless because at any time I, the output bit yi is a stochastic function of just xi. Okay, so the channel as such has no memory about the previous input bits or the previous output bits. It just looks at the current input bit and decides in a stochastic manner what the output bit is going to look like. Now, this is a very well-studied class of channels, beginning with the work of Shannon. And Shannon in 1948 put down the capacity of this channel, which is given by this expression here. What is the capacity? The capacity, as we know, is the maximum rate at which we can reliably communicate information over this channel. Okay. What do we mean by reliably? It means that the probability of error, that is the probability with which m is not equal to m hat, really goes down to 0 as n goes to infinity, as the block length goes to infinity. And Shannon showed that this really is the maximum rate at which you can send messages across this channel, where the rate has something to do with the maximum number of messages that you can send across the channel. Okay, so the expression here is max over probabilities p of x of the mutual information between the bit x and the bit y. So note that this is a single letter optimization problem. Okay, so let us just keep that in the back of our minds right now. Now, what we'll do right now is we will segue to a setting with a little more added complexity, which is the setting of a DMC with feedback. So now there is a feedback link from the decoder back to the encoder. What does this feedback link do? It basically sends the bit yi at any time I that the decoder sees with a unit delay back to the encoder. Okay, so now the encoder knows more than what it did in the case without feedback. All the same, Shannon proved in 1956 that this was a pessimistic result, that the capacities with and without feedback are in fact identical. Okay, that there is no increase in the amount of in the number of messages that you can send with feedback as opposed to without feedback. Okay, so which specific channel are we interested in? This is called the binary erasure channel. The binary erasure channel has binary inputs 0 or 1, and it has ternary possible outputs, okay, 0, 1, or question mark. And any particular input, say 0, is either received as such or is received as an erasure. This is a very common model for modeling erasures in storage media, etc. So let us put this binary erasure channel into our picture. And what is well known is that you can just plug in the binary erasure channel in the expression for the capacity with or without feedback, and you will get that both these capacities are the same and they are equal to 1 minus epsilon, where epsilon is the erasure probability. It is the probability with which you get an erasure given that the input bit is either a 0 or a 1. Okay. But although feedback does not increase the capacity as such, it does allow for a very low complexity capacity achieving coding scheme. And in this talk, our main attention will be on the design of low complexity coding schemes. Okay, so by coding scheme, we mean the joint action of an encoder and a decoder. And we would primarily be interested in those coding schemes whose rates are equal to the capacity. Okay, so these are the high rate coding schemes whose rates actually achieve capacity. Now, as is the case with the simple binary erasure channel with feedback, feedback actually allows for an extremely simple capacity achieving coding scheme. And we'll describe what that coding scheme is now. This is just the repeat until success scheme that we are all familiar with in, say, over simple communication networks as such, where, you know, as the same bit is sent over and over again until it is received successfully. So how does that look like? So again, let's have the binary erasure channel in the center. Suppose we want to send a bit 0, okay, and we send it successively, we keep sending it until it is received successfully. Okay, so now the bit 0 is received successfully. Now it is easy to verify that the distribution of the number of channel uses that are required to send a bit successfully is geometrically distributed. It's a geometric random variable with success probability 1 minus epsilon. Okay. And so the rate of such a coding scheme is just 1 bit in every 1 by 1 minus epsilon channel uses, right? Because 1 by 1 minus epsilon channel uses are on average the number of channel uses that are required to convey 1 bit successfully. So 1 by 1 minus epsilon gives us 1 minus epsilon, and this rate actually equals the capacity. Okay, so this scheme is capacity achieving, and this is an inordinately simple coding scheme which can be implemented in practice also. But our goal right now is to look at more complicated classes of channels and take inspiration from this coding scheme in order to derive capacity achieving coding schemes for those channels. So, yeah. So what are the kinds of channels that we are interested in? So these are the broad class of input constrained discrete memoryless channels with feedback. Okay. So the system model looks something like this. It is almost exactly identical to our previous setting, only that we now have a constrained encoder. Okay. So earlier we just had an unconstrained encoder. Right now the encoder is constrained to produce sequences, to produce input sequences that obey some hard constraint. We'll tell you what those hard constraints are in a little while. Now, for such a general class of input constrained DMCs, it is well known from the work of Yang and co-authors, and even from slightly earlier, that the feedback capacity is given by this expression here. Okay. Now, the difference between this expression and, say, Shannon's expression are that the expression that you see now on the slide is a multi-letter optimization problem. Okay. It involves a limit as n goes to infinity, etc. And hence, this is intrinsically very hard to compute. And harder still is the task of getting good coding schemes, good feedback capacity achieving coding schemes for this channel. Okay. So let us again recap the fact that we are interested in the input constrained binary erasure channel with feedback. And what is the specific input constraint that we are interested in? It is the so-called D-infinity run length limited input constraint, or the D-infinity RLL constraint. So what does this mean? It means that the constrained encoder must produce binary sequences xn such that, you know, in the sequence xn, between any pair of successive ones, you have at least d zeros. Okay. For example, you know, for storage on Blu-ray discs, for storage on the earlier CD-ROMs, etc., d was roughly of the order of 3 or 7 sometimes. The value of d is specified a priori, and we need to, you know, design capacity achieving coding schemes that are based on this knowledge of d. Okay. So for example, if d equals 2 for the 2 infinity run length limited constraint, this particular sequence that you see here does not respect the constraint because, you know, you have a 101 as a substring, which does not respect the constraint. Whereas this sequence right here indeed does respect the constraint. Okay. All right. So we've spent a fair bit of time explaining what the channel model is and explaining some motivation behind this. So let's get to what our goals are. Well, firstly, like I mentioned, we want to compute the feedback capacity of a BEC with this particular D-infinity run length limited constraint. And furthermore, we want to get to good capacity achieving coding schemes that achieve the feedback capacity. And in turn, it would be nice if these coding schemes are low complexity, and an even higher ideal that one could try to attain is that these feedback coding schemes are zero error. Okay, and as we will see, we can indeed attain both of these goals in this talk. So the big highlight of this talk is going to be the coding scheme, the feedback capacity achieving coding scheme. And time permitting, we will be speaking a little bit about codes for the setting where there is no feedback. Okay, but that is again dependent on how much time is taken by this capacity achieving coding scheme business. Okay, so let's get ahead. There's a lot of prior work in this field. I've listed very recent work, but really the literature on feedback capacity goes back a long way. I mean, there was the earlier work of Cover and Pombra, I think in 1989, and then there was Shalkwick and Kailat's feedback capacity achieving coding scheme for the Gaussian channel. But for discrete channels of this kind, you do have the work of Oron Sabag, Chaim Permuter, and Navin Kashyap, who explicitly derived the feedback capacity of the binary erasure channel and some binary symmetric channels with a no consecutive ones input constraint. And the manner in which they did it was using some dynamic programming based methods. Later on, Oron Sabag and co-authors came up with a method of deriving good bounds on the feedback capacity using input distributions that are supported on graphs. Okay? And we will be seeing a little bit about these kinds of bounds in this talk also. And finally, such bounds were used by Peled, Sabag, and co-authors to actually derive the feedback capacity of the 0K RLL input constraint binary erasure channel. What is the 0K constraint? It's just the sister or the dual of the D-infinity constraint. It says that you can have at most K zeros between every pair of successive ones. Okay, whereas the D-infinity constraint was that you must have at least D zeros between every pair of successive ones. Okay. And finally, we had last year some bounds on the feedback capacity with the D-infinity input constraint. But right now, we've actually solved for the capacity explicitly, feedback capacity explicitly, and that is what we'll be covering in this talk. So our main result is really quite simply stated in one theorem. The feedback capacity of the D-infinity RLL input constraint BEC looks like this expression here. Now, the expression looks intimidating, but it actually really pops out quite nicely or elegantly from the coding scheme that we're going to describe. Okay. Note that this is an inordinately simple D+1 parameter optimization problem. Okay. So unlike the multi-letter optimization problem that we were seeing at the start of this talk, wherein you had a limit as n goes to infinity, etc., here you just have a numerical optimization problem that depends on a fixed number of parameters. In this case, D+1 different parameters. Okay. And furthermore, there exists a simple labeling based coding scheme that in fact gets a rate that is equal to this feedback capacity. Okay. So this plot here shows us the different values of the feedback capacities for different values of D. As you can see here, these are nice concave curves. We really don't know why these, I mean, there's no clear explanation for why the feedback capacity must be a concave function of epsilon, but that is how things have been turning out for these input constrained erasure channels. Another interesting thing to note is that if you look at the feedback capacity at epsilon equals 0, that is at along the y-axis, you will see certain numbers. For example, for the blue curve, its value at epsilon equals 0 is roughly 0.69. So what does this value mean? Well, when epsilon equals 0, it tells you that there's no noise whatsoever in the channel. Okay, that whatever you send is received exactly as such at the decoder end. So the only constraint, that is imposed on the output sequences, and there's no noise in the channel, is the input constraint itself. Okay, and you can have only as many output sequences as are permitted by the input constraint. So for example, when d equals 1, it is called the 1 infinity input constraint. It is very easy for you to verify that the 1 infinity input constraint just means that you need to have at least 1 0 between any pair of successive ones. Or in other words, you cannot have consecutive ones. There is no consecutive ones input constraint. Now for this no consecutive ones input constraint, what is its noiseless capacity? That is its capacity when epsilon equals 0. It is well known from elementary combinatorial methods that this noiseless capacity equals the log of the golden ratio, which in turn equals 0.69. Okay? And it has things to do with the rate of growth of the Fibonacci sequence, etc. And similarly, for d equals 2 and d equals 3, we can verify that whatever we get from our expression exactly equals the noiseless capacity when epsilon equals 0. Okay. So now let's get ahead to describing our coding scheme, which must be the highlight of this talk. This coding scheme differs from the standard kinds of coding schemes that one might possibly see in a error control coding class, wherein the emphasis is primarily on linear codes, etc. So here we are going to describe a coding scheme, a feedback coding scheme that has no linearity structure, but that uses a fairly interesting representation of the messages as points on the 0-1 interval. Okay, so let's get to the specifics. So recall that we want to send a message across this channel. Okay, so we pick a message M from a set of capital M number of possible messages, and we pick this message M uniformly at random. And for each such message M, we associate with it a point on the 0-1 interval. So you stretch out the 0-1 interval in front of you, and you map each message M to the point M over M. Okay. So the points corresponding to the messages run from M equals 0 up to M equals M minus 1 at points 0 up to M minus 1 over M. And what we do is we design d+1 different labeling schemes. Okay? d+1 different labelings. Now, what is each labeling? So we have the unit interval in front of us. The unit interval is peppered with points which represent messages. And we are going to split the unit interval into subsets that are labeled 0 and subsets that are labeled 1. Okay? And the label of any subinterval is used to determine the input bit that is to be sent. We will describe how that scheme goes on in a little while. So for now, you can see the manner in which we have constructed these d+1 different labelings are that we first choose d+1 different parameters, delta naught, delta 1 up to delta d, that satisfy this constraint that the sum over all the delta I is less than or equal to 1. Okay. Then on the right, if you look at any one of the labelings, you will see that for any labeling Li, the interval that is labeled by, so for example, if you pick L2, the interval that is spans delta naught plus delta 1 to delta naught plus delta 1 plus delta 2 is labeled by a 1. And same way we extend this labeling scheme to all the d+1 different labelings, basically just moving the interval that is labeled by a 1 diagonally across. Fine. So how do the rounds of transmissions go like in this coding scheme? So like I said, we use the labelings to select the input bit that is to be sent. And how do we do that? So let us start at time t equals 1. Okay. So this is the start of transmission. And all that the encoder has right now is knowledge of the message that needs to be transmitted. So suppose, for example, that the message that needs to be sent is message number 3. Okay, and we have colored this message number 3 in black on the slide. So if you look at, so we start with labeling L0. So the encoder looks at L0 and sees where this message number 3 is located. Okay. And it sees that it's located in a subinterval that is labeled by a 1. It then says, all right, let me then set x1 to be 1. So this decides the first bit. Now let us examine what happens when this bit is actually sent across the channel. And in particular, our first concern will be with the case when the bit is received successfully at the decoder. Recall that this is an erasure channel. Okay, so if you send an input bit, it is either received successfully with probability 1 minus epsilon, or it is received as an erasure with probability epsilon. Okay, so let us consider the first case when we receive the bit successfully. So we are sending x1 equal to 1, and suppose y1 equals 1 also. So what does the decoder know now? It knows that the encoder started off with labeling L0 and that it has received a 1 successfully, which means that those messages that are labeled by a 0 in this L0 labeling could not possibly have been transmitted. And why is that so? It's because the binary erasure channel has no probabilities, has no crossover probabilities between 0 and 1. So if it has received a 1, it knows for a fact that the input bit that was sent must be a 1. So it focuses attention on only those messages that were labeled by a 1, and it spreads out those messages uniformly over the 0-1 interval. Okay, and that is what is shown on this slide. Now recall that we are working with a constrained encoder. Okay, and in particular, the encoder must respect the D-infinity input constraint, RLL input constraint. Again, what that means is that if you ever send a 1, it needs to be followed by at least D zeros. So let us do something. So let us set the next D inputs to be zeros. So what we have specified until now is first we know what the encoder does at time equals 1. It just looks at the message and sends the bit. We know what the decoder does at the end of time equals 1. It focuses its attention on just those guys that are labeled by a 1. And now we are specifying what the encoder must do for the next D time instance, which is precisely the fact that the encoder must send D zeros. Now note that in this sort of an interim juncture, when the encoder is sending zeros in order to respect the constraint, the decoder knows that the encoder must be doing this, okay? Because it has received a 1 successfully, and it knows that the next D inputs must be zeros in order to respect the input constraint. So there's no real information that is gained by the decoder when these zeros are being sent in order to respect the constraint. Okay. So let us now consider the other situation when the bit that is sent is received as an erasure. It is received unsuccessfully or incorrectly. So let us take, for example, that we are starting with labeling L0, and the message is message number 4, such that the first input bit is a 0, as you can see here. So x1 is a 0. And x1 is received unsuccessfully, so y1 is a question mark or an erasure. So now, what does the decoder know? Well, the erasure symbol in the binary erasure channel is such that either of the input symbols could be equally likely to have been sent. Okay, so with probability half, conditioned on the fact that it has received an erasure, the input bit could be a 0, and with probability half, the input bit could have been a 1. So the decoder has no additional knowledge about what the message could have been. So all that it does is it moves to the next labeling. It retains the set of messages as such and moves to the next labeling. And note that both the encoder and the decoder carry out this operation because now you have feedback. So once the decoder receives an erasure, it moves to the next labeling L1, and then it sends this erasure back to the encoder. Okay? In effect, telling it also to move to the next labeling L1 without really changing the set of messages that we are focusing on. So the way you should really think about feedback in general is as a signaling mechanism that allows for an adaptive coding scheme between the encoder and the decoder. So the job of the encoder is to somehow lead the decoder into agreeing with it on the set of possible messages, okay, which is what this scheme does. Now, again, if you see here in the labeling L1, so now it's the encoder's job to again send. It again is working with message number 4. And it sees that the label corresponding to that message is 0. So it sends a 0. So x2 is a 0. And suppose, for example, that x2 is also received as an erasure. Okay, so x2 is also received unsuccessfully, or that y2 is an erasure. So now again, what the decoder does is it knows nothing more about the message. It goes to the next labeling, which is L2. Okay, and so does the encoder. But now what happens is that now that we have moved between labelings, at the encoder end, at time instant number 3, the labeling corresponding to message number 4 is now a 1. And this is where, I mean, there are a lot of places where this coding scheme differs from the simple repeat until success scheme. But if you recall, in the repeat until success scheme, you are sending the same bit over and over again. Here, you're not sending the same bit. You're sending a certain bit that corresponds to the same message over and over again. Okay. So now x3 is a 1 corresponding to labeling L2. And let us say that y3 is a 1. Okay, that y3, that x3 is received successfully. So then according to our previous scheme, what must the encoder do? It must just focus its attention on those messages that are labeled by a 1. Because it has received a 1 successfully, so it knows that only a 1 could possibly have been sent. But amazingly, the number of messages that are labeled by a 1 in L2 is exactly 1. There's only one message that is labeled by a 1 by the label 1 in L2. So now when the decoder spreads this one message onto the 0-1 interval, it notices that there is only one message. And so it has uniquely identified that particular message that was intended to be sent by the encoder. So now there's a unique decoding here and the transmission ends. And the end of transmission could be signaled by any other symbol, not in the output alphabet. And hence, this coding scheme that we have is a zero error coding scheme, which means that with probability 1, the decoder always decodes the message that was to be transmitted successfully. Okay, so this is a higher ideal than what we had started off with, which is the usual Shannon capacity framework, wherein you allow for an epsilon n probability of error for any block length n, and then you let epsilon n go to 0 as n goes to infinity. But right now, at some finite block length, we don't know what that block length is because it's a variable length coding scheme. But at some finite length, the decoder is indeed able to successfully decode what the input message was with probability 1. All right. So now that we have specified a coding scheme, all that remains is an analysis of what its rate is. Okay, so a coding scheme is only as good as its rate. And if this coding scheme has a very trivial rate, then it's of no use. In order to analyze what the rate of this coding scheme is, the most easy thing that one could start off by doing is trying to see what the probabilities are that are used to assign 1 at any time instant, an input of 1 at any time instant. So note that all through in our coding scheme, we've been using these d+1 different labelings. And in each of these labelings, for example, in labeling, say, L2, the length of that interval that is labeled by a 1 is exactly delta 2. Or in other words, for any labeling Li, the length of an interval that is labeled by a 1 is Li. Is delta I.
Vishnu has a question.
Yeah, yes.
Yeah, Vishnu, go ahead and ask.
Hello.
Yeah.
Yeah, in the first, in the initial slides, you said that when the bit is correctly received, what happens there? I mean, when there are when there is not a unique message, so what would you do there?
Yeah, when the bit is received successfully, so you are labeling either by zeros or ones, right? So suppose let us assume that the bit that you were intending to send is a 0 and that you receive a 0 successfully. So then what the decoder does is it chucks those messages that are labeled by a 1. Okay, because a 1 could not have been received as a 0 at the decoder end. It's an erasure channel.
Yeah, again it starts labeling. Again it asks for sending it until unique message.
Okay. Yeah, that's right. So across time instance, you're always monotonically. So if you look at the set of possible messages that could have been sent, you have a monotonically decreasing sequence for the cardinality of these sets, monotonically non-increasing sequence. So that is the set of possible messages can never increase. Set of possible messages that could have been sent based on the decoder's knowledge can only decrease as time goes.
Yeah, got it. Thanks.
All right. So now, as you can see, and as was pointed out, in any labeling Li, the length of the interval that is labeled by 1 equals delta. So now, using some elementary arguments, you can then set the rate of this coding scheme. Okay, this can be made formal, but I'm just giving you sort of an intuitive explanation for this. You can set the rate of the coding scheme to be somewhat like the expected number of bits per successful transmission divided by the expected number of channel uses that you use to send a bit successfully. Now, suppose you fix the numerator to be 1, that is, you're receiving exactly 1 bit successfully. You can compute what the denominator is. Okay? And these computations are relatively easy to carry out. And you will get that the rate is given by this expression in red at the bottom of the screen. Okay? And since we started off with some parameters delta naught to delta d that obey some constraint that summation of delta I is less than or equal to 1, you can in principle just optimize over all these delta i's. Okay? And it gives you some rate. So we have a rate in our hands, it's a non-trivial rate. So what this tells us is that the feedback capacity is lower bounded by this rate. Okay, because we have just established an achievability scheme. We have shown you a coding scheme that has this rate. So the feedback capacity can only be larger, if at all. But as it happens, we can actually arrive at an upper bound which equals the lower bound. Okay. And the manner in which we do this in our work is that we rely on this certain very novel technique of Sabag and co-authors, of Oron Sabag, Chaim Computer, Henry Pfister and co-authors, wherein they use the idea of a graph-based input distribution. Okay, I'm just going to very briefly describe this, not going to get into the details because this is sort of specific to this kind of a domain. It doesn't extend to other, say, continuous channels, etc. So the idea is this. So all through in the setting with feedback, what does the encoder know? What is the encoder's view? The encoder intends sending a bit xi at any time I. But what does the encoder know at time I? It knows all the input bits up to time I minus 1 that it has sent. The encoder has all that memory. But in addition, you have feedback. So it knows all the previous received output bits. Okay? So really the action of the encoder in some sense is the probability P of xi given x up to I minus 1 and y up to I minus 1. Okay, but this is far too difficult to handle because you can have extremely large memory for the encoder. So let us just focus. So the idea of this approach was that one could just focus on those input distributions that have some finite memory. Okay, those input distributions that depend on only, say, finitely many of the previous outputs. And if you just draw out what these previous outputs are going to look like, you will immediately see that you can represent them as nodes in a graph. Okay? And this graph is what is called a Q graph, or a quantization graph of the output sequence. So I'm not going to get into the details of what this Q graph is, etc. But the thing is, in our work, we show that if one were to use a Q graph that is shown on this slide, that is, if one were to use input distributions restricted to those that are supported on this Q graph, or in other words, if one uses input distributions that depend only on, say, d+1 of the previous outputs, then the feedback capacity is upper bounded by the expression on the right. But as we showed, the feedback capacity is also lower bounded by the same expression, and so this expression equals the feedback capacity, and the lower bound was via the coding scheme. So we now have a tight expression for the feedback capacity. This is an explicit characterization. And in tandem, we were also able to explicitly identify a feedback capacity achieving coding scheme, okay, which is A, low complexity, and B, zero error. Okay, so we have achieved both the ideals that we wanted to achieve when we started out. Now, this feedback capacity problem of the D infinity RLL input constraint erasure channel was a fairly well-known open problem in information theory. And this really concludes, or this really finishes off that problem in its entirety. Okay. So we now have a little amount of time left. So what I intend doing is talking a little bit about the setting without feedback. Again, not much of the details here. But really, see, the thing is, any communication system, any communication link in the real world is going to be such that you always have a feedback link, mostly, except, storage channels. Okay. So, for example, if you're communicating with a satellite link or etc., we know that the downlink is generally more reliable or has greater fidelity than the uplink and so on. But there are situations where you need to communicate without feedback, where the encoder does not know the previous outputs that have been received up to that point. So what does one do in such a setting? Now, in the setting with feedback, the reason why we were able to develop this really nice adaptive coding scheme, okay, there have been a whole host of adaptive coding schemes. I must mention that the Schalke-Kailak scheme is possibly the first one of those. There's also a Holstein scheme in the 1970s, etc. And there was this entire generalization called the posterior matching principle that came out in roughly 2008, which unified all of these schemes. And our scheme that we have presented here is also a specialization of the posterior matching principle to the input constraint binary erasure channel. Okay. So anyhow, so for the setting with feedback, the reason we were able to do all these nice things is that inherently the problem of computing feedback capacity and the problem of designing feedback capacity achieving codes is a stochastic control problem. Okay, wherein you can think of the encoder as being some kind of an agent in a Markov decision process, and at any time it's taking actions. It's deciding it's deciding with what probability it must send the next input and so on, based on all the knowledge of the outputs also. Okay, so this is a closed loop stochastic control problem, and hence this really fits into the well-known paradigm of, say, using Bellman equations to solve for feedback capacity, etc. But for the setting without feedback, this is an open loop problem. You don't have the feedback link. So the encoder must decide in a sort of blindsided manner what the next input must be. So what can we do in this setting? So just to recap, what is the channel model that we're dealing with? Until now, we have just been focusing on the discrete memoryless channel, no feedback here. And we know what the capacity looks like. Okay. So what this slide endeavors to do is to just replace the DMC with a general channel model, which is called the finite state channel, or an FSC. So what is an FSC? It is a channel model in which the current output yn at any time n depends not just on the current input xn, but it also depends on something called the state of the channel up to that point. Okay? And this state you can think of as some function of finitely many previous outputs or finitely many previous inputs and so on. Okay? So this is a general class of channels. There are other channel models that look very similar to the finite state channel model. There are things called the arbitrary varying channel, etc. But this is a general enough class of channels to model several communication settings, etc. And it is known from a very early work, some of which can be found in, say, Gallagher's book. It was written in 1968. Is that the capacity of such a finite state channel is given by this expression here. Okay. For those who have seen this expression before, this is called the maximum of a mutual information rate. Okay. So actually, I'm missing a limit as n goes to infinity here. Okay, so it must be c equals limit as n goes to infinity of the maximum of this expression. So again, you have a limit as n goes to infinity, etc., which makes this problem really intractable. And as such, this has been a very wide open problem in information theory. There have been no solutions till date of explicit characterizations of the capacity without feedback for even simple channels like the binary erasure channel. Why is it so complex? It is because of this factor. So suppose you had an input constraint at the encoder. So for simplicity, let us assume that you have some d infinity input constraint or the 1 infinity input constraint, which means that you can't have successive ones. Suppose you were to use even a simple input distribution like a Markov input distribution. Immediately, the output distribution becomes hidden Markov. Okay, and so the problem of computing the capacity without feedback is equivalent to the problem of finding the maximum entropy rate of the output process. And this is a very well-known hard problem. So these two problems are exactly equivalent for the case of certain channels, and their hardness is implied by the other's hardness. It is hard because, there are multiple reasons, but really one can, until now, people have only been successfully bound these, the entropy rate of such channels. There has been no explicit expression for the entropy rate, for the maximum entropy rate of a hidden Markov process. All right. So what do we do in such a setting? So we need to try to achieve something in the setting without feedback. So let us at least try to get something numerically. Okay, so I'm running out of time, so I'll just explain in short what our idea is. So again, we just focus on Markov input, first order Markov input distributions. Okay. So once you restrict your attention to certain classes of inputs, immediately it becomes known that what you're really driving for is a lower bound. It's an achievable rate. Okay, because you don't know what the structure of the optimal input distribution is going to look like. You're just saying, okay, let me just focus on this particular class of first order Markov distributions, of ergodic first order Markov distributions, and try and see what I get, what rates I get. And it is immediate that the actual capacity is lower bounded by this first order Markov capacity. And our goal right now is to see how we can compute this CF, which is the first order Markov capacity. I'm just going to give you a sketch here. So in our recent work, we have actually been able to get an explicit expression for CF for the 1 infinity RLL input constraint erasure channel. Okay, and that expression is given by the massive thing that you see on the right side there. The structure of this expression, although a little intimidating, immediately suggests that one could try a stochastic approximation scheme or an RL scheme, a reinforcement learning scheme, in order to learn the best possible input distribution. Okay, so all through we are working with in the class of parameterized first order Markov input distributions, where the parameter is described by this A that you see. So we want to guess the best A. Okay, and we are going to get there via a reinforcement learning scheme, or a reinforcement learning algorithm, or a stochastic approximation scheme, etc. I'm not going to display the algorithm here, but I'm just going to say that the essence of this algorithm is just that it is a gradient search based algorithm. It takes in knowledge of this first order capacity expression. It also takes in a certain first order Markov input distribution that we are working with. And then it uses simple sample based gradient search. This is using some known techniques in stochastic approximation in order to obtain explicitly an approximation to the first order capacity. Okay, all these are numerical, but still, these are good things to know, because when one designs actual encoders, etc., one needs to know what is the best Markov input distribution that one could work with, or what is the best input distribution until now that one could work with. Okay. And in addition, what this RL scheme also gives you is that it gives you knowledge of what the optimal input distribution is. Okay, like I said, which is the best thing that an algorithm designer could have. And what I'm going to show here are some plots of our results. So the curve that you see in green is precisely the achievable rate via this RL scheme, or the stochastic approximation scheme. And as you can see, the green curve is extremely close, is tantalizingly close to the dotted red line that you see there, which is an analytical upper bound on the capacity without feedback. Okay, so the green line is a lower bound, the red dotted line is an upper bound. And you can see that these two are inordinately close. Okay, so we were able to actually get really good rates, really good achievable rates, by using just simple first order Markov input distributions without feedback. And what's more is that we are actually able to identify what the optimal distribution is going to look like. So this plot really shows you a sketch of what the optimal parameter in the first order Markov distribution is going to look like. It's shown by the line in blue. And as you can see, our stochastic approximation algorithm gives us rather smoother estimates than those that are obtained via vanilla sampling based schemes, etc. But the one thing that we must add is that there are multiple avenues to just improve upon this stochastic approximation scheme by just using sophisticated, say, neural network architectures, etc. But really, just vanilla gradient search coded up will give us the optimal input distribution directly. Okay. So we have gotten to the end of the talk. What have we learned, and what is the road ahead? Well, just to summarize what we have seen until now, for the setting with feedback, we were able to actually get a promising coding scheme, a low complexity coding scheme, which got to feedback capacity and which is eminently implementable. And for the setting without feedback, what you have seen is that we have an RL algorithm, or a stochastic approximation algorithm, that gets really close to the purported capacity without feedback. Purported because we don't know what the capacity is, we just know upper bounds, and the upper and lower bounds are really close. So what is the road ahead? We want to design good feedback coding schemes in general for channels that have application in, say, wireless communication. For example, intersymbol interference channels or flat fading channels, etc. And we also want to improve on the knowledge of our coding schemes for the setting without feedback. So without feedback, all that you have seen until now are algorithmic techniques. These specify what the encoder must do, but what the decoder must do is essentially just maximum likelihood all over again. And as we know as communication engineers, maximum likelihood is a difficult thing to carry out precisely. Okay, it's a complicated algorithm, and even for simple binary symmetric channels, etc., maximum likelihood is the same as the nearest distance decoder. And again, you're going to do exponentially many such searches. Okay. So you want to get away from this. You want to design sort of explicit codes that have polynomial time complexity. Okay. And we are right now trying to do that using known families of codes. In particular, what our recent results show us is that if one were to use the read mother family of codes, then one can actually get to non-trivial achievable rates over the erasure channel with the d-infinity input constraint. Okay. So this work is still going on and it's in progress. Yeah, and that really concludes the talk. Thank you for listening. I'm open to questions if any.
Thank you, Arvind, for the interesting talk. I hope it would have really intrigued people working in similar or even in different research areas. We are open to questions. Are there any questions? You can unmute yourself or put in the chat box. Arvind, can you stop sharing?
Yeah, sure.
Yeah, Vishnu, go ahead and ask.
Yeah, basically the first coding scheme which you have described using feedback, where is it explicitly? Is it used, or in what sort
Which?
of the BEC one? Initially you have described it, right? The labeling.
What is being used? Feedback.
No, the coding scheme which you have described. The capacity achieving coding scheme.
Yeah, I don't understand what is being used. So feedback is being used, right?
No, you have designed a coding scheme, right? The
Yes,
LZO
yes,
labeling stuff.
yes,
That
yes,
is,
yeah.
in what applications is it used? Can it
Oh,
be?
I mean, we have
Yeah.
just designed the coding scheme.
Yeah.
Okay, the
I mean,
yeah,
what
the
what was it?
application, yeah, yeah. So the applications really are go like this. It is a storage application, but
Mhm.
like I
Yeah.
pointed out, storage channels are not. I mean, they're not really feedback channels. But there are other, for example, the sort of at the start of the talk, we had a small discussion on DNA-based computation and storage channels. So any channel where you have a simple NAC or an ACK being received as feedback, you can actually use this coding scheme. But such input constraints are primarily found. Such hard constraints are primarily found in storage channels where you don't get these. So what one must ideally look at this as is, okay, the feedback capacity. So this gives you a handle on what the capacity is without feedback, because the feedback capacity is an upper bound on the capacity without feedback, and it's a non-trivial upper bound. Okay. So besides that, I'm not really sure what I mean, you can, there are of course these situations where, even in storage, if you're going to store it bit by bit, etc., and you're going to get acknowledgements, then yes, there too. But yeah, that is about all that there is.
Yeah. Thanks.
But this is a fundamental sort of open problem in information theory, these channels with hard constraints.
Yeah, hi. This is Vinay. I had a question. So, in the coding scheme that you explained, so it seems to depend. Okay, so first of all, there was this unit delay for the feedback, and yeah, so the encoder uses the information to send the same message. So there, I mean, have you done some delay analysis kind of thing for this?
When the feedback has, say, a delay of k or something.
No, not exactly. I mean, so, I mean, how does it perform with, no, since there is a unit delay, so this might get compounded. So these relative values of your D and your number of messages M will play a role, right?
No. So when I mean unit delay, it's just that before sending xi, it's going to have yi minus 1. Okay, so even in our feedback scheme, we are using only yi minus 1 to send xi. So the unit delay is just a pedantic thing. I mean, you can't.
Okay.
So if you denote what the output is by yi, you can't have received yi itself.
Okay.
Before sending xi.
Okay.
But yes, you raise a fair point in the sense that what does the feedback capacity look like when you have delayed feedback? Okay, when you have non-trivial delay, not just unit delay, say delay of k. That's an open thing. That is something we could look into.
Okay.
So, are there any more questions? Feel free to ask. Okay, so if there aren't any questions, okay, thank you once again, Arvind, for delivering this talk, and please accept this memento on behalf of IEEE-IISc Communication Society and IEEE-IISc Signal Processing Society.
Thank you.
We wish you all the best in your future endeavors.
Thank you.